Welcome back to the Learning Studio. You're watching our mathematics series, where we uncover the deep structures that power science, technology, and artificial intelligence. If this is your first time here, don't forget to follow us by clicking the link below. And remember, the full playlist is also in the description, so you can explore every episode in order. Today, we're diving into a field that explains how systems evolve over time, from the orbit of planets to the beating of your heart. This is dynamical systems and chaos theory. It's the mathematics of change, motion, and sometimes unpredictability. Here's a famous saying: a butterfly flaps its wings in Brazil, and weeks later, a tornado forms in Texas. This is the essence of chaos theory. Small changes in the starting point can lead to huge differences in the outcome. But chaos doesn't mean randomness, it means complexity. Systems that follow rules yet produce behavior so sensitive and intricate that it feels unpredictable. And understanding these systems is one of the greatest achievements of modern mathematics. Core concepts explained simply. Here are the essentials. Dynamical systems. These are systems that evolve step by step or continuously over time, following specific mathematical rules. They can be simple, like a swinging pendulum, or complex, like weather systems. Nonlinear systems. Many real-world systems are nonlinear. Their parts interact in ways that don't add up simply. This nonlinearity often leads to rich, surprising behavior. Chaos theory. In chaotic systems, tiny changes in initial conditions explode into vastly different outcomes. The system is deterministic, but its future is practically impossible to predict. Applications. Dynamical systems are used in physics, biology, economics, robotics, and climate science. Chaos theory helps us understand turbulence, ecosystems, and even the rhythm of the human heart. Why it matters in AI and technology. Dynamical systems in chaos aren't just fascinating theory, they're vital for modern technology. In robotics, dynamical systems control how machines move, balance, and adapt. In neuroscience, the brain can be studied as a nonlinear dynamical system. In climate modeling, chaos theory shows us why weather is so difficult to predict. Even in artificial intelligence, ideas from dynamical systems help us design recurrent neural networks and adaptive models. This field teaches us that the world isn't static, it's in constant motion, and mathematics is the key to understanding that motion. So dynamical systems and chaos theory reveal the hidden order behind complexity, showing us that even in apparent randomness, there are deep structures at play. In our next episode, we'll move into stochastic processes, where randomness itself becomes the object of study. From Markov chains in Brownian motion to reinforcement learning in AI, we'll explore how mathematics models uncertainty over time. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode brings us closer to seeing mathematics as the ultimate language of both order and chaos.